Hello learners, and welcome to the very last discrete math lesson called Infinite Series. The definition of an infinite series is an expression of this form. On the left we have a Riemann sum that starts from the first term and never ends, denoted by the infinity sign. And on the right we simply have a sum of terms, and we know that they're infinite because of the two sets of ellipses in between the second term and the nth term, and after the nth term. So it goes on forever. Mathematicians of the 17th, 18th, and even 19th century were very curious about infinite series, especially when the sum of an infinite number of terms ends up being a finite number. So I invite you to be curious along with them and me. Let's start with the idea of partial sums. A partial sum is a finite sum of the first n terms. So we're talking about 3, 4, maybe 5 terms. Sometimes that sum approaches one number, the idea of convergence. Sometimes the sum approaches infinity, meaning it grows without bound, and we could see that just in the first few terms. Or it approaches two numbers, like an alternating series, negative, positive, negative, positive. Let's take a look at an example that includes one of each of these situations. For the following three partial sums, find the next two terms and tell whether the series appears to converge or diverge. Number one, we have three terms there already, and I see that it's 0.1, 0.01, 0.001, so I'll write down the next two terms. The fourth term has 3 zeros before the 1. The fifth term has 4 zeros before the 1. I'm starting to notice that these numbers are approaching 0, which means that the sum is going to converge. But you might not believe me. You might be thinking, well, isn't that going to end up being infinity? Well, what this number ends up being is 0.11111, and so on forever. So that sum approaches 0.1 repeating. Number two. We have 10 plus 20 plus 30 plus 40 plus 50 plus numbers keep getting bigger and bigger. This does not converge to one number, and therefore this diverges. I'll also say in parentheses infinity, that sum approaches infinity. All right, number three, we have 1 minus 1 plus 1 minus 1 plus 1 minus 1, and this goes on forever. It's like yes, no, yes, no, yes, no. And this is an idea that represents divergence as well. And that's because the sum is approaching two numbers. Think about this. The partial sum of the first two is 0. Then the first 3 is 1. And then the first 4 is 0 again. So the sums are 0 and 1. So what is it? Is it 0 or 1? It can't be both at the same time. So that concept is diverge. And like I said a few moments ago, this is an alternating series because it has positive and negative numbers. It's bouncing between the two. And we study that in Calculus BC. The sum of an infinite geometric sequence, well, that's called a series. An infinite series, because in this case we'll be talking about an infinite sum. Okay, in words, if the common ratio of a geometric series is between 0 and 1, then the series converges and has a sum. Just like the mathematicians that came before you, you can verify this by just playing around with the numbers and a calculator, and you could see that the sum approaches one number when you have an R value that's less than 1. Okay, so as a theorem, if the common ratio, the absolute value of that common ratio is less than 1, because R could be 1/2 or negative 1/2 or 3/4 or negative 3/4, then the geometric series that's infinite, it converges. That's pretty cool. It's pretty amazing actually. And it converges to one sum, and that sum is the first term divided by 1 minus R. And sorry, I'm not going to go into detail as to why this is. Again, we could play with the numbers to verify the formula. I have one example of finding the sum of an infinite geometric sequence. Phew, it's a mouthful. Determine if the series converges. If it converges, give the sum. We have the Riemann sum from 1 to infinity of 2 times 0.25 to the k minus 1. Okay, 0.25 is 1/4. The first term is 2 times 1/4 to the 1 minus 1. Now, 1/4 to the 0 is 1, so therefore the first term is 2. The second term, now I don't have to do all of that again. I know that 0.25 is the r value, the common ratio, so r equals 1/4, and a, the first term, is 2. So I could find the solution already, but let me just write out a few terms just so I know what's going on here. 2 times 1/4 is 2/4, which is 1/2. And then the third term, so 1, 2, 3, this is the term. 1/2 times 1/4 is 1/8. Ah, this is kind of fun. I like that. Let me do the fourth term here. So this is 1/8 times 1/4 is 1/32. And the fifth term is 1 over, what's 32 times 4? 64 times 2, 128. Now, what I can see with these terms is that these terms are getting quite small. And if you get to the 10th term or the 20th term, we're adding a really insignificant number. So we're expecting this series to converge to one number, meaning the sum of the infinite series is one number. So the solution to that is, first of all, r, is that less than 1? Question mark. Yes, it's 1/4. Therefore, the sum of the infinite series is 2 over 1 minus 1/4, which is 2 over 3/4, which is 2 over 1 times 4 over 3, which is 8/3. That is wild. It's wild that you could add up an infinite number of numbers and get a finite number, which is 8/3. That is the sum of an infinite number of numbers. Wow, that's wild. It's curious. That's interesting. I hope you think so too. Well, thank you so much for joining me on this discrete math journey. Think about all the memories we made together. We spelled words with your name. We realized that a locker combo is actually a locker permu. We learned about Pascal's triangle. And we didn't play the lotto. Wow, good job. And we didn't join the bachelor or bachelorette. We listed numbers in order, just like the old days in middle school. And then we added those numbers together. Wow. The probability that you enjoyed our journey together is about 50%. Yes or no? Whether it was yes or no, I wish you all the best in your future math endeavors. Bye-bye.